Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, we'll be continuing non-parametric methods in Chapter 6, looking at both two-sample procedures and a one-sample example where the non-parametric methods greatly outperforms the classical t-test. So when we have two samples that we want to compare the means or medians for, if our model assumptions for a two-sample t-test are not met, recall that is that the sampling distribution of the difference in means is normal. So if that sampling distribution is not normal, then this is one alternative, the Wilcox and Mann-Whitney test. And the assumptions, there are assumptions here in the non-parametric method. And here's an illustration of what that looks like. They should have your two populations that you're comparing the means or medians for should have the same shape, and the only difference should be the location. So for example, on the left we have basically two normal distributions that are offset, that have the same shape but are offset by some amount, maybe 6 or 7 units, whereas on the right we also have two distributions that have the same shape and are offset by some amount. And in this case, because we don't have symmetric distributions, we want to compare the median, but we can compare them using this procedure because we have those same shapes. So if we have skewed distribution, that's fine, but we want skewed distributions with roughly the same spread. And so we might look at the interquartile range for an estimate of the spread of those distributions. Okay. All right. So the Wilcox test in R is where to get some help on this. And the basic idea is described here in this paragraph. All right, so while the exact calculations of the procedure is a little bit, differs a little bit from this, this is the basic idea. So the procedure is based on ranks, just as the Wilcoxon sign rank test that we had earlier in this chapter for a one sample test. But in this case, we're going to combine our two samples, and we're going to rank all the values from both samples from smallest to largest. And then once we have those common ranks, then we're going to separate them back into the original samples. And if the two populations have the same medians, then the average rank of the two samples should be roughly equal. Effectively, the values from sample 1 and sample 2 should be roughly interleaved to each other, almost like a good shuffling of a deck of cards, where because they've got the same distribution and the same median, they should have the same location overall. So all the quantiles or ranks should match up between the two distributions. All right, and then we perform calculations to assess how similar the average ranks are between the two distributions. All right, so let's look at an example having to do with meteorites, in particular the cooling rates of meteorites, and we'll see this example again in or actually we've already seen it back in Chapter 5 for more samples. Here we're looking at the Uwet and the Walker County meteorites. Uwet comes from Nigeria and Walker is in Alabama. And right, meteorites come from space, so in a way it doesn't matter what part of the Earth they landed on. But we're going to take measurements from each of these meteorites to get an estimate of the cooling rate of the meteorites. Right, so when the meteorites are formed, quite honestly, I don't know how that happens, but they're rocks, they're flung out into space somehow, and they're really hot when they're formed, and then they slowly cool. And we want to know what that cooling rate is, how many degrees per million years or something. So a primary interest here is in the population typical cooling rate measurements. So here are the two meteorites. Each of them has a series of measurements that, based on a physical model of meteorites, these are the estimates of the cooling rates for these meteorites. If we take a look, I'll just scroll on down to the plot. On the left, we have the cooling rate along the horizontal axis and the Walker and the UWet sites. And you can see that these data have basically the same shapes. They just differ by the median cooling rate. The two QQ plots on the right indicate that the data are not normal. You can see the U-shape pattern of the black points indicating that right skewness. And so I'm going to probably be hesitant to apply a two-sample t-test here. We haven't looked directly at the sampling distribution of the difference in means here to check whether it would be okay, but I don't know, given these two outliers, I'm skeptical that it would look good. So let's take a quick look at the UWet summaries and the Walker summaries. In particular, how about the interquartile range? Just to have a sense of whether these are roughly equal. So about 0.26 and about 0.2. So those are not very different. The main thing that's differing is the medians of 0.25 versus 0.1. All right. All right. So here is the t-test, the two-sample t-test, and here we're just putting in the two individual vectors, and we're assuming that the variances are equal, given that the standard deviations are not that far from each other. I don't know. It'd be fine to say that we have unequal variances as well. In fact, that's what's done below. Anyway, just to take a look at this one, here's a p-value 0.11, and a confidence interval goes from -0.6 to 0.57. So we fail to reject the null. It seems that the means of these two groups are equal if we're fine with the model assumptions. Even if we assume that the variances are not equal, we have the similar conclusions, p-value of 0.13 and a fairly wide confidence interval from 0.08 to 0.6 almost. All right, but given that non-symmetric distribution, let's take a look at what the Wilcoxon-Mann-Whitney two-sample non-parametric method gives. All right, so here we're asking whether the median of these two distributions are equal or not. We have a p-value of 0.049. Okay, so it's less than 0.05. It's about a p-value as close to 0.05 as you'll ever see, and a confidence interval that goes basically from 0 up to 0.45. Okay, I'm going to skip ahead a little bit. Oh, nope, that's the end of that example. Okay, so one set of comments here is about the appropriateness of the t-test. Okay, we're probably not appropriate because of the skewness, and what the effect has. So notice when we use the t-test, which is the most powerful test when our assumptions are met, here the assumptions aren't met. We have a p-value that's 0.11 and quite a wide confidence interval. The confidence interval is about 0.63 or 64 in width, whereas the non-parametric method has a p-value that's half the size, 0.05, and a confidence interval that's about 2/3 the width, 0.45. So because we used the appropriate procedure, we had more power for the hypothesis test and a narrower confidence interval. All right, let's see a second example of that. In this case, we'll look at a famous example from the late 1800s where Newcomb wanted to understand the speed of light. And so he had this cool diagram here, or a cool setup. These were, let's see, it was a mirror. Let's see, there was a light going from Fort Mayer on the west bank of the Potomac. It would cross the river over to the Washington Monument, bounce back from a mirror, and come back to the place where they had the light coming from. And so here is a diagram of that setup, but in this case we've got a laser. Okay, if we were to reproduce this, we've got a laser shining at a rotating mirror. It hits a lens, reflects off a stationary mirror, comes back, hits the rotating mirror, but now the rotating mirror has moved because of that distance traveled, and so reflects at a slightly different angle and comes back to where the laser was projecting from, and that difference in distance, if we know the speed of the rotating mirror, gives us some and the total distance, right? That gives us some information as to what the speed of light is, how long it took to travel that path. So cool setup. And here is an example where we have a fairly big sample size, right? So here are all the observations. We've got 6 observations by 2, 4, 6, 8, 10, 11. So we have 66 observations here. Fairly big sample size. If we take a look at the normality of these data, they're far from normal. And finally, of course, take a look at the plot of the data, and you'll see some obvious issues with this data. Almost all these observations follow, a beautiful distribution, looks basically normal. But then we have these couple extreme observations, which might be measurement errors. Maybe the rotating mirror, slowed down or sped up. I guess it would be sped up in this case. And so this is a real issue. So if I was the experimentalist here, I would definitely go back and try to understand why these two measurements occurred. And if I could find a reasonable explanation for why they are systematically different from the conditions for the rest of them, then I would remove them. But if not, I would probably keep them as part of the experimental data, because that's part of the evidence that I have. Just taking a look at the QQ plot of the data, you can see those two observations on the left being very, very different from normal. On the right is the bootstrap sampling distribution of the mean. The data is on the top, and the bottom is the sampling distribution of the mean. You can see that right skewness, that systematic under, over of the black curve that fits the sampling distribution relative to the red normal distribution. And so this is a case where I would feel really uncomfortable using a t-test if we're going to include those two outliers in the data. All right, so here's the t-test, and what I'm doing here is I'm outputting the confidence interval. There's the confidence interval. If I look at the difference of the values in the confidence interval, this is the width of that interval, 0.005. Okay. Let's compare that to the other nonparametric methods we've seen for one sample data. Here's the sign test and the Wilcox sign rank test. And if we put all that into a single table to see how these methods vary in their inference, here are the confidence interval limits, and here's the width of the intervals. And you can see for the t-test, because we have that left skewness, the width of this interval is more than twice what both the sign and the Wilcox sign rank tests give us for the confidence interval. So my main emphasis here is to indicate that nonparametric methods are powerful methods. When the t-test is not appropriate, the nonparametric method is going to give you good inference, and often better inference than the t-procedure. And so that's the conclusion of this whole section. All right. So we've learned about two-sample Wilcox-Mann-Whitney test and the sensitivity of using the t-test when you shouldn't, and that nonparametric methods are really the ones you should be using. All right. When we come back, we will look at analysis of variance when we have more than two samples that we are comparing the medians for.